Welcome back, Apologia, 8th grade physical science, week 25, day 1, textbook pages 413 to 416, notebook pages 342 and 343. Experiment 11.3, current and resistance, will be done in class, but it is simple enough that if you would like to do it at home, really you need a AA battery, 1.5 volt battery, and some aluminum foil. But if not, we will definitely do this one in class. Conductors and insulators. Have you ever wondered why metal wire is usually coated with plastic or rubber? You already learned that metals are good conductors of electricity. Remember that metals make positive ions easily by giving up electrons. It turns out that metal ions form a type of lattice structure where their loosely bound valence electrons can easily move back and forth. This is illustrated in figure 11.19. This is why electrical conductors are materials through which electrons can easily flow. The plastic or rubber coating are electrical insulators. Electrical insulators are materials in which electrons cannot easily flow. The coating around the wire helps to keep the metal's valence electrons where they need to be. The coating also protects you from getting a shock when working with the circuit. Now that you know how to get electrons moving by using an energy source such as a battery, and that metal wires are good conductors of moving electrons, you might be wondering what actually happens to those electrons as they move through the wire. And how can we use the energy in the electrons to do work, which is something useful? Well, once you get electrons moving using an energy source, the electrons move through the conducting wire, as you see in figure 11.20. As they move, they collide into other electrons and the ions in the wire. Remember that energy of movement is kinetic energy, so the moving electrons have kinetic energy. As they collide, some of the kinetic energy is converted into thermal energy, which can be used to do work such as cooking. However, now that some of the kinetic energy has been converted, there is less energy available to move electrons through the wire, which means the current will be reduced, and this is called resistance. Resistance is specifically defined as a material's ability to impede the flow of charge. All right, that brings us to experiment 11.3. And again, you use a 1.5 volt battery. Any AA, C, or D cell battery will work. Do not use any battery other than those, because a higher voltage can make the experiment dangerous. And also we needed a little bit of aluminum foil. I did this at home. We will also be doing it in class. The heat you felt in the experiment comes from the electrons moving in the foil. As soon as you touched the aluminum foil to both ends of the battery, electrons flowed through the aluminum from the negative side of the battery to the positive side. The electrons accelerated under the electromagnetic force of the battery and, as a result, started moving quickly. Now, as electrons flowed through the aluminum, they began colliding with the electrons in some of the aluminum atoms. They also collided with the impurities in the metal. These collisions produced heat, and you felt that heat in your fingers. So the heat you felt in this experiment was a result of the aluminum resisting the flow of electrons. Each metal resists electron flow differently. Therefore, each metal has its own specific resistance. It turns out that the type of metal is not the only thing that determines resistance. The resistance of a wide piece of metal, for example, is lower than the resistance of a narrow piece made out of the same metal. Think about it this way. Which straw would be easier to drink a milkshake through? A tiny little thin straw or a thick, wide straw? It is definitely easier to drink a milkshake through a wide straw. In the same way, a thick wire allows the electrons that move through the metal to spread out as they move through, reducing congestion and thus the number of collisions. Two other things besides thickness affect resistance. As you might expect, the longer the metal wire, the larger the resistance. After all, the longer the metal, the more chance the electrons have to collide with things in the metal. Finally, temperature will affect resistance. As the temperature of the wire increases, more electrons can collide more often. Because electron collisions increase, resistance increases too. With the knowledge of current, electrical circuits, and resistance that you now have, let's look at how the simplest electrical devices work. For example, consider an electrical heater. This could be a space heater used to warm up a room, a coil on an electric stove, or even the wires on the inside of a toaster. When such a device is turned on, the heater begins to glow, emitting a large amount of heat. This works because the material used to make the heater has a certain amount of electrical resistance. Since there is resistance, there is heat and often light. The light causes the heater to glow, and the heat energy warms the room, cooks the food, or even browns the bread. One way we get electrons to do something useful in an electrical circuit, then, is to use a metal's resistance to convert the kinetic energy of the electrons speeding through the circuit into thermal, heat, and light energy. The type of metal used to do this will influence the effect you get. For example, most metals will resist the flow of electrons in such a way as to produce mostly heat and only a small amount of light. Those metals are used in heaters, stoves, and toasters. Other metals tend to produce more light than heat, and those metals are typically used in the filaments of light bulbs. It is important that you really see what's going on in an electrical circuit. Most people think that electrical devices use up the electrons. Thus, you plug your appliance in and it eats up the electricity it pulls from the electrical socket. That's not what's happening. The same number of electrons flow out of a toaster as the number that flowed into it. What the toaster does use up, however, is energy. As electrons flow through a circuit, the collisions they experience convert the energy produced by the electromagnetic force into heat. On your own, 11.6. When we work with most circuits, we assume that the resistance of the wire in the circuit is zero. Thus, the only resistance we consider is that of a device or devices in the circuit. Suppose a wire was made of aluminum. Would it have zero resistance, and how do you know? All right, the wire would not have zero resistance. In this experiment 11.3 that we did with the battery and the aluminum foil, you actually felt the heat as the electrons traveled through the aluminum. The only way that heat could be produced is through resistance. Thus, the aluminum foil had resistance, and in fact, all wires under normal conditions have resistance. Nevertheless, though, we typically ignore the resistance of a wire in an electric circuit because compared to the devices in the circuit, the resistance of the wire is very, very small.